So thanks everyone for coming today. Looks like we got a great turnout today. It's my pleasure to introduce Kevin Schaefer. I think a lot of you know Kevin. Of course, he's been at NSIDC in one form or another for quite some time, right? He's still with us. We do a lot of work together. I've been pleased and honored to be in the field with Kevin a few times, like up near Yellowknife, Alaska, and up outside of Fairbanks, places like that, looking at permafrost and tracing through the Boreal forest of the north, all good times, right? And Kevin, as you might imagine, is one of our leading experts in permafrost, right? And today we're going to hear all about estimating permafrost depth in the Yukon-Kuskokwim Delta using Lidar. So Kevin, you have the podium.
Thank you very much. As Mark said, I'm Kevin Schaefer here at the National Snow and Ice Data Center. And today I'm going to talk about estimating permafrost thickness or depth in the Yukon-Kuskokwim Delta using Lidar. We got a very strong team, very creative people, and I'd like to thank all of them. Some of you may not be as familiar with permafrost, so I wanted to go over a little bit of background just so everyone's talking the same language. Permafrost is permanently frozen ground at or below 0 degrees centigrade for at least 2 consecutive years. The active layer is the surface layer of soil that thaws in the summer and then refreezes in the winter. And permafrost degradation is any kind of decrease in the extent of permafrost or the thickness of the increase in the thickness of the active layer, or in this case, I should have added it here, any change in the or decrease in the thickness of the permafrost layer itself. Now, this is a typical permafrost profile. This is exposed by thermal erosion due to melting ice wedges on the north slope. And you can see at the very top there a couple fingers of someone holding the tape measure. I forgot who it was. And this particular area, the active layer is only about 35 centimeters thick, and I've labeled it there. This particular column is kind of like an alternating, organic layer and silt layer, organic silt. And it turns out this particular area underwent episodic flooding, and every time there was a huge flood, put a layer of silt down, and then the organic or the plants would regrow again, and it would result in this alternating layer. But this is kind of a typical profile, just to give you some background. And some more background so we understand what thickness is. This is a schematic, a theoretical diagram, and on the horizontal axis we got temperature. And you can see right in the middle there is a 0 degree temperature line. And the yellow vertical lines are supposed to represent temperature as a function of depth. And you can see here at the surface, there's a Y shape, and that's the annual cycle of freeze and thaw. And you can see, the active layer is defined there as where it crosses. I don't know if you can see my cursor, but that's the permafrost table represents the deepest part of the active layer. And the middle line represents kind of an annual average, and this represents how cold it gets in freezing. And so when deeper it gets, the warmer it gets, and when the temperature finally crosses 0 again, you get the permafrost base. And we're defining permafrost thickness as the depth from the surface to the permafrost base. Now, the thickness of the base, or the permafrost thickness, is essentially a balance between freezing from the surface and warming from the Earth's interior. And so it varies with space and time. And to illustrate that, I'm going to take a transition or a transect of the Mackenzie River. Now, this is a map showing permafrost distribution in the northern hemisphere. And you see a red line there right through Canada. And that represents the Mackenzie River basin, you might say. So this line pretty much goes right down the center of the Mackenzie River Valley. And this is the theoretical thickness of the permafrost. On the left, you have the Arctic Ocean, and on the right, you got the border with Alberta. And you can see it's thickest right along the Arctic Ocean because that's where it's coldest. Here, the estimated depth is around 700 meters. In parts of Siberia, it could be as along the Arctic coastline. It could be as deep as 1,500 meters. Now, as you go south, which is to the right here, the air temperatures get warmer and warmer, and the permafrost gets thinner and thinner. Eventually, it transitions out of the continuous zone into discontinuous permafrost, and finally, away south, sporadically distributed permafrost. Now, what we're trying to do in the Yukon-Kuskokwim Delta is actually calculate the depth of this blue line, and we're in a discontinuous zone. Now, let's take a look at that. This is a Google Earth image of the Yukon-Kuskokwim Delta. And you can see in the north, you got the Yukon River. And on the south, you've got the Kuskokwim River. And right in the middle is probably the largest town in the area, Bethel. Now, the interesting thing about this, I'm going to put it in the yellow line. This is the domain of what we're trying to do here. And in this area, you got to understand the morphology to understand what we're trying to do. So I want to take a close-up picture. This is an aircraft view, and we did some survey work out here with probes and ground-penetrating radar. And the geomorphology of this area consists of raised peat plateaus separated by sunken thermokarst gullies and wetlands. Now, what happens is the formation of the peat allows for freezing of permafrost below it. And as the permafrost freezes, the ground heaves up. And soil, when it's fully saturated, it expands around 4% when frozen. Now, our surveys indicated, yeah, underneath the peat plateaus, there's definitely permafrost. In the thermokarst gullies and wetlands, there is no permafrost, or at least we couldn't detect it. And so this is what we're seeing here. So essentially, the geomorphology of the area is pretty much driven entirely by the formation of permafrost. And so the heights of these peat plateaus are actually proportional to the thickness of the permafrost itself. And to illustrate what we mean, I brought some pictures of some of our field work. On the left, we got Roger Michaelides, and he's standing on top of a peat plateau that borders a lake. And if you look in the far distance, our camp is on the far side of the lake. And what you see is this rises up around 3 meters, and you can see the plateau, just extending around into the background. And it's pretty uniform here. It's about 3 meters high. On the upper right is a picture of us trying to drag our ground penetrating radar unit out of a thermokarst gully. This particular gully, they tend to be flat on the bottom, but we're trying to get out. It's about 3 meters deep, and we're trying to heave it up the wall of the gully. And we chose this particular spot because the transition into and out of the gully was a little bit wider, so it wasn't as steep. But you can see in the background here, this is what it normally looks like. It's actually pretty steep, almost a wall about 70 degrees or so. In the lower right, we see Andy Parsekian analyzing some data, and you can see right behind him is the wall. The height of this plateau is around 3 meters, and you can't quite tell here, but because of the perspective, but right behind him, it pretty much drops 3 meters straight down to the edge of the lake. So this is kind of what we're seeing here. And so the height of the peat plateau is proportional to the thickness of the permafrost. Now let's look at some LIDAR data. And this is from the ISAT-2. One of the ISAT-2 products is height. And I'm just showing one beam here because it's several beams, 3 sets of 2 beams, but I'm just showing one beam. And you'd notice the arrow here north. I tipped it 90 degrees just for artistic reasons so I could show this. But on the bottom here, well, you can see that this beam, it definitely crosses, a couple raised peat plateaus that are separated by sunken wetlands. And on the bottom here, you can see in yellow the height as a function of position. And what we need to do, what we're trying to do is we want to calculate the height of the peat plateaus relative to the sunken wetlands and gullies. And that height is proportional to the thickness of the permafrost. And I show 2 examples here. You can see the middle part right here, it skirts the edge of a wetland, but never doesn't quite get off it. So you see a dip And what we want to calculate are these heights. Now, how do we do that? This is a typical section of a typical Lidar swath or MITESAT-2. It shows height as a function of position. On the horizontal axis, we got latitude here. I didn't put distance. I probably should have converted this to distance, but it doesn't really matter. And on the vertical axis, you've got the altitude. Now, notice the variation here, between, just over, 15 and a half to 17 and a half, like a 2-meter range in this particular section. And this is very typical. This whole delta is really, really flat. I mean, almost pool table flat. And so we're looking for actually pretty small variations between the gullies and the raised peat plateaus. So this is a typical product. The first thing we did was apply an algorithm that identifies local minimums. And these local minimums, theoretically, are the thermokarst gullies themselves. The next thing we do is we connect these local minimums to get what I'm calling is the thaw height. Now, this is the height of the surface if all of the permafrost instantaneously thawed. In other words, it's the height of the topography of the surface without any permafrost whatsoever. And so we're assuming by connecting the thermokarst gullies that we're going to get a pretty good idea of what that background topography, that thaw height, would be. So we do that and we get the blue line right here. Now, I wanted to point out that we still have some issues here. For example, right here around the top here, it detected some, local minimums, but is that really a thawed gully? Should it really connect these bigger lines here? A little vague here. There's some issues here we're going to work on. But anyway, we take the blue line and we subtract it from the original heights, and we get this. Now, this is essentially representing the height of the peat plateaus right along the line of the ISAT-2 line. You can see here it puts zeros right in the thermokarst gullies, and the heights here in this case vary between 0 and 1 meter. Now we take these heights and we apply a soil expansion model. Now this model essentially is a model of porosity of soil as a function of depth, and we assume saturated soil, which is a pretty good assumption here. And it allows us to estimate the expansion due to freezing, and that allows us to calculate the depth. And that's what we see here. Now here, the depth varies from 0, which is the thermokarst gully, up to about 25 meters, or rather, I would say 5 meters. These smaller plateaus are roughly 5 meters thick. Now let's take a look at some data. I chose about 30 or 40, actually I chose about 70 lines, and I threw out a whole bunch of lines that had basically mostly cloudy. With LiDAR, if you have a cloud, you're not seeing the ground, so I just threw those out. But I took them and I calculated the heights, or rather the thickness of the permafrost along each line, and then just put them onto Google Earth here so that I could visualize them. And here's a more oblique view of that. Notice the crisscross pattern, each of these. What I did is I created what I call a wall in Google Earth. And the height of this wall is proportional to the estimated thickness of the permafrost. There are some issues here, and I think I'm going to have to do some cropping. These are the areas I outlined here in red represent what I would call false topographic signals. This technique works only in areas where the formation of permafrost itself dominates the topography. And so if you get mountainous areas that are dominated by other geological processes, you're really not getting a real signal here. You're just getting a false signal. And so I'm going to have to do some filtering to remove those false signals just by basically cropping out the areas. Now this is a close-up of one of the walls, and you can see here the height of the wall is proportional to the thickness of the permafrost. And you can see that the action of the peat plateaus. For example, right here, it crosses a lake and it goes to zero because there's no permafrost underneath the lake. And then it gets thicker as the peat plateaus get high. And then when it crosses thermokarst gully, it again drops to zero. And you see that all over here. So when you see these humps, they represent the, individual individual raised peat plateaus. So the technique actually works pretty well. However, there are some issues. This is not, perfect.
Hey, Kevin.
Yeah.
Siri Joda has a question. What dates are the IS2 data from?
They're from 2021. I know that, but I would have to look up the exact dates of the lines. As you might imagine, there are a whole bunch of lines. There's probably 2,000 or 3,000 lines or more that cross this area. And I only took a subset of those. And I would have to look up the exact dates. Yeah.
My curiosity was whether it went through seasonal changes, if there's any reason to expect it would be different at different times of years, the results. And since they're repeat tracks, did you compare the same track, at the more or less the same time of year, and did you get some of the results? That was just
yes. So I did restrict this to August. I was trying to get, the what I would call near the deepest part of the thaw of the active layer. I did look at, repeats, quote unquote. I want to put those in quotes because I actually looked at repeat swaths and they do not overlap exactly. And so that's a little bit of a challenge. And there's also the idea, yes, you could probably take a time series of these if you can get a good enough repeat and probably deduce the surface subsidence as the active layer thaws. It's a challenge though, because the accuracy you need to measure that, which that kind of substance is only about 3 to 4 centimeters, but the accuracy of the Lidar is about was a couple meters. I'd have to look up the exact value.
Excuse me, Kevin. Can we just finish the presentation?
All right.
And not diverge to this kind of technical questions, because there's much more serious questions to discuss here.
All right.
Be ready, Kevin.
Okay. There are some issues with my results. For example, there's an area that has a large amount of sand dunes, and these are basically formed by O'Learian dust deposition. So it's not really formed by the formation of peat. These side lines, the ice lines cross over each other, but I don't always get the same values. So I got to figure out a way to make sure that they actually match up when I do this. Also, every so often you get some bad data, and this is what it looks like. And I got to figure out a way to filter out the bad data because it really doesn't help me that much. Other issues, more with technique. This is I'm missing, in this particular case, I'm missing the edges of the gully. It finds a local minimum right here, but it really should extend this zero values out to the edges of the gullies. And you can see that I'm not quite doing that here. And so because I think I'm getting a little overestimated here. Also, in this case, there's the idea I'm getting too many local minima. This is a fairly large plateau, and my algorithm is finding local minima, all right, but they're not necessarily in the thermokarst gullies where I would want to locate them. And so I'm getting false zeros. And I got to figure out how to deal with that. After we looked at this, we decided that we could actually apply this technique to a digital elevation model as well. And so what we did is we did some test areas, and this is just a randomly chosen test area near where we actually did some survey work. And on the left, you can see a Google Earth image. Yeah, there's thermokarst gullies, there's wetlands, there's lakes. And in these areas, there's no permafrost. And then it's separated. These are all separated by raised peat plateaus. And from that, I was able to deduce maps of permafrost depth. Now you notice here that there's a lot of striping, horizontal and vertical striping. And that's because I took my algorithm to find local minima, which is designed for a line, a Lidar line, and I applied it to a two-dimensional map, and it didn't always work out perfectly. And so, you know, we're exploring how to do this in a way that would be a little cleaner. Now, some statistics on the left is that they, you know, basically a histogram of what ISAT gets, and on the right is a histogram of what the DEM gets. And there's just a lot more data with the DEM, and that probably accounts more for the shape difference. But, you know, if you look at the median values for the ISAT-2 and the DEM, they're actually pretty close to one another. ISAT-2 is estimating a median value of 39, and DEM, we're getting a median value of 45 meters thick. And, you know, you could see some really high values for the ISAT-2, you know, 75 percentile. Well, that's caused by the bad data, which throws in a whole bunch of really, really deep values that just are not real. And I haven't filtered those out yet. So what we're doing now is we're going to take a look, exploring the DEM route a little bit better. We think we can do it cleaner. Now, this is on the left is a typical terrain that you'd see in the YK Delta. And on the right is a digital elevation model. Now, I didn't put in the physical scale here because I forgot. But, you know, this is, you know, the topography here, difference in the lows and the highs is no more than 4 meters or so. So it's pretty flat. But what we want to do is we want to locate all the thermokarst gullies in a way that is accurate. And we recruited some experts on this. And what we're doing is an image processing technique called segmentation. And I'm not going to pretend I know all the details of this, but basically on the left, we've got a cross section through a typical gully. And what we're trying to do is, you know, essentially model or curve fit this step function to the data itself. And from that, locate the center of the gully and the walls of the gully. And that tells us the locations of the gullies. And on the right, what you see here is a kind of map. It will work on making it pretty, but it's showing the edges of all the thermokarst gullies and the wetlands and the lakes. And from that, we calculate what's called a skeleton, basically locating all the thermokarst gullies. And yeah, so we get a skeleton. This is essentially the center lines of the gullies. And you can see here, located on top of the DEM, that it does a really good job of locating the DEM. And now at this point, we haven't completed this yet. We're still working on it. But at this point, what we got to do is calculate the thaw height, which is the theoretical surface height if all the permafrost instantaneously thawed out. In other words, the background topography. And we're going back to Lidar data to try to do this. So we're figuring out how to do it. We haven't done it yet. But basically in Lidar, you've got Lidar, you know, point clouds where it bounces off the surface that you're trying to detect, but also all the objects that are sitting on the surface. And we show here, for example, buildings and trees. And what you do is you flip it over and put a theoretical cloth or a model cloth on that, and that would allow you to estimate the height without the objects on it. And this is taken right from the paper. In the middle, there's a bunch of buildings. And in our case, instead of trying to remove the buildings, what we're trying to do is remove the raised peat plateaus. And you can see on the right is the results of what you would get, you know, the surface without the objects on it. And for us, this would be the theoretical thaw height, the height of the surface without permafrost on it. So in conclusion, this is the first time anyone's been able to try to use remote sensing to get the permafrost depth, the thickness of the permafrost. The results look reasonable compared to cores. There are a couple cores. People drilled some cores in the YK Delta, and this compares quite well to those few single values. The ISAT2 and the DEM actually produce pretty similar results. And the next thing we're trying to do is we're trying to finish this network algorithm where we're trying to locate the gullies and the thickness of the gullies. And we're going to apply this to the entire DEM for the YK Delta. And what we're hoping to do is, we're going to do it with the DEM, and we're going to figure out a way to use the Lidar to kind of monitor the permafrost. In theory, the Lidar should be able to detect, substance due to thaw, thinning of the permafrost layer itself. So I think that's it. Oops, that's the end of the slideshow. Thank you very much. I really appreciate you all looking, and